Hello, welcome to this video on exam technique. So in this video we're going to look at the EDEXCEL Unit 1 paper. So this is the legacy paper, but it's still quite useful because we're still looking at the exam technique side. And the whole point, like I say, of these videos is to go through and look at the answers for them, work through them and find out why they are their answers. You can actually look at the mark scheme, but the mark scheme doesn't actually explain how it got the answer. So the aim of this video is to make sure that you know how we've got it, and also throw in a few hints and tips as well along the way to make sure that you can answer the questions successfully as well. Now, as you can see on the side of this video, there's menus where you can skip to different questions in this paper, so feel free to click on them if you want to skip to a particular part. So as you can see, this is the chemistry EDEXCEL Unit 1 paper, and these ones EDEXCEL start with multi-choice questions first. So look at this first one. So it says answer all the questions in this section. You should aim to spend no more than 20 minutes in this section, and all the usual stuff at the top there. So the first one, it says the correct sequence for the process of the processes that occur in a mass spectrometer is, so this is the one you've really got to know, and the answer is actually A. So it's vaporization, ionization, then it's accelerated through plates, deflected through a magnet, and then it's detected at the end as well. So this first one is actually going to be A. So we're going to put the mark on there. Okay, the second question, just nudge that up there. Which of the following ions would be deflected the most in a mass spectrometer? So basically we're looking for an ion that could have a potentially double charge. This is going to be deflected more, affected by the magnetic field more. So this one's going to be 2. Okay, and then question 3. It says a particle with a single positive charge and with the electron configuration 1s2, 2s2, 2p6 is, so if we think about this, this has lost an electron because it's a single positive charge. So this is something that had an electron before but doesn't anymore in the outer shell. So this has got to be a sodium ion. Fluoride ion wouldn't form this configuration. You need to look at the periodic table for that one to make sure that is correct. Okay, right, so there you go. There's your first 3 questions. And the next question, question 4, it says, in which of the following electron configurations are only 2 of the electrons unpaired? So this is basically trying to test your understanding of electron configuration. You can see here, if I draw our s orbital, and then we've got our p orbitals, which occupy 3 separate blocks. 1s2, 2s2 means you'd have 2 electrons in there, and the 2s2 means they fill up singly first, so that one's not right. This one is 1s2, 2s2, 2p3. Again, you can see here that we have 3 unpaired electrons for this one here, so B isn't right. If we come into this next one, 1s2, 2s2, 2p4, 2p4 means that we have 1 paired electron if this is the p orbital, so put 2p up there, and you can see here there's 2 that's unpaired. So therefore this one must be the right answer. Let's see. Okay, question 5. Which of the following contains a dative covalent bond? Nitrogen is a normal covalent, so nitrogen would look something like this with 3 bonds. NH3 would be 3 hydrogens sticking out like that. NH2 minus would just have something like that and have a negative charge. There are no dative covalent bonds there. So it's got to be the last one, which is NH4 plus, 3 hydrogens, and the last one, because the lone pair of electrons on there, would be a dative covalent bond, which is there. So the answer is the last one, which is question 5. Question 6. So it says, which of the following ions has the largest ionic radius? This one's quite tricky, actually. As we go across the period, the ionic radius generally gets slightly smaller. However, we have an increase here. These ones only have s orbitals. These ones have p orbitals. So actually, it's between these two because we have a higher orbital. And the biggest one is actually going to be this one here. Fluorine is smaller because it has 1 extra proton, which kind of tucks in the the shells a little bit more. So the answer is D, which is O2 minus. Okay, and then looking at question 7, says which of the following observations provides the best evidence for the presence of ionic bonding in an unknown substance? So with this one, we're looking at, obviously it's ionic, so in a solid state it won't conduct, in a solid state it doesn't conduct electricity, in the solid state and when molten, again solid state doesn't conduct electricity, so the only one left is only when molten, but not in the solid state, so that's the final one, which is D. Okay. Right, so on to question 8. So it says which of the following can be determined for an unknown alkene using only percentage composition by mass data. So with this one, if we've got percentage composition, that basically tells us the ratio of elements in the molecule, and that is a classic sign of an empirical formula. So actually this one is going to be B. So yes, that's the one there. Okay, so this is not the molecular formula because we need the molecular mass to work out the molecular formula. Structural formula, you would need the same as well, so it has to be empirical. Okay, number 9. This is the maths bit. There's quite a bit of maths in this little bit here. So 1.12 grams of iron react with oxygen to form 1.60 grams of an oxide of iron. Use the relative atomic masses. Fe 56, O is 16, and we have to work out the formula of this oxide of iron. So the first thing we need to work out is we have Fe, and we're going to react that with oxygen because that's what we've been told. We've also been told that 1.12 grams of iron reacts with a certain amount of oxygen. Now we can work out the amount of oxygen by taking 1.60 away from 1.12, and that should get us 0.48 grams. Now here we're just working out the empirical formula effectively. So we take the mass and we divide it by the MR of each of them. So MR of Fe is 56. And of oxygen, we're only looking at one molecule of oxygen because it's an empirical formula, although oxygen does go around as a pair. We're just going to put 16 in there. And then what we need to do is we then put both of these into our calculator, and I've worked these out previously, so we should get 0.02 on that side, and then 0.03 on that side. Divide by the smallest number of moles either side, so the smallest number is 0.02, so that should get us a ratio of 1. That one's 0.02, and that should get us a ratio of 1.5. We double these two, so we should get a ratio of 2 to 3 for iron and oxygen. So a 2 to 3 ratio would leave us with D, which is Fe2O3. There you go, and that's how you work that out. So this is just empirical formula effectively. Okay, so the next question. It says question 10. In an experiment, 1.226 grams of potassium chloride, KClO3, was heated. A mass of 0.320 grams of oxygen gas, O2, was collected. And they've given us the equation here. Use the molar mass of KClO3, which is this, and the relative atomic mass, which is oxygen, which is 16. The percentage yield of oxygen in this experiment is. Right, so now because we want to work out the percentage yield, and what we have to do is work out the theoretical yield and then work out the actual yield that we've actually gathered. So the actual yield is pretty straightforward. All we have to do is just work out the number of moles of oxygen. We've been given the mass, which is there. Okay, so it's 0.320 grams. And we can work out the relative atomic mass, which is 16, which is of oxygen. Remember, we've got 2 of these, so that has to be 32. And so therefore, the number of moles of oxygen that I worked out previously, just before, you should get the number of moles of oxygen to be 0.01. So remember, when you're working out percentage yield, you must use the number of moles. So this is the number of moles of oxygen. This is the theoretical. This is the actual yield. And then what we have to do is work out the theoretical yield of oxygen that can actually be produced. So what we have to do is actually work out the number of moles of this first. So we can see that we have the number of moles. I'm going to put KClO3. So the number of moles is the mass over the MR. Now we know the mass because we've been told that we had this amount of mass. So that's 1.226 divided by the MR of this, which is 122.6. Now, if we put that into our calculator, we should get a total mass, or we should get the number of moles, should I say, of 0.01, which should be the same as that. But crucially, what we have to do is divide this by 2 to find 1 mole, and then multiply that by 3 to find the theoretical moles of this. So if we divide that one by 2 first, so bring the calculator over, 0.01, divide that by 2, and we should get 5 times 10 to the minus 3, and then we're going to multiply that by 3 because we need to work out the actual number of moles of oxygen, which is 0.015, as you can see on there. So this is going to be the, so let's put that on there, and then times it by 3. So that's going to be 0.015. So this is the theoretical amount. So all we have to do is we take the actual divided by the theoretical, times it by 100, and we should get our yield. So we'll put this over here, 0.01 divided by 0.015, and then if we times that by 100, we should get this as our actual yield, which is 66.7%. So there's quite a bit to do for that one. The idea is you must work out the actual number of moles of your product that you're producing, and then your theoretical. But in this case, we had to use the molar ratio in the equation to work that out. So there you go. Okay, so the next one. Okay, so this is number 11. So drag that there. So it says oxygen gas, O2, can be converted into ozone, O3, by passing it through an electric discharge. So we've got the equation here. It says in an experiment, a volume of 300 centimeters cubed of oxygen was used, but only 10% of the oxygen was converted into ozone. All volumes are measured at the same temperature and pressure. All right, so this one again is quite a tricky one to work out. But the first thing we need to do is work out the moles. That's normally the standard thing. I like to say, if in doubt, work out the moles. So that's only if you're stuck, of course. So the moles is oxygen. The moles of oxygen, should we say, is the volume of gas divided by 24, because that's the volume that it would occupy at standard room temperature and pressure. So the number of moles, the volume that we had at the start of oxygen was actually 300, and we're going to divide that by 24. And again, I've worked this one out already, so this is 12.5, and this is the number of moles of oxygen. So then we're going to work out the moles of ozone, and this is assuming that all of it converted. We'll deal with the 10% later. And all we had to do is effectively, this is the number of moles of oxygen. If we divide this number by 3 to get 1 mole of oxygen, multiply by 2 to find the number of moles of ozone. If all of it converted, like I say, then that would be 8.33. That's what we should get. And then if we work out the volume, so the volume, if we rearrange this, is the number of moles times by 24. So that's going to be 0.833 times by 24. And we should get a volume, if we round it, of 20. So now this 0.83, I should mention where we've got this number from. Because it said we had 10% of the oxygen was converted into ozone, this is the number of moles if 100% converted. So all I've done is I've moved the decimal point back one place, and this represents the number of moles if 10% had been converted. Multiply it by 24, because that's the volume of gas. That's the volume that a gas would occupy under standard conditions, and that gets us 20, which is centimeters cubed. So that's how much ozone was produced. Now we know that 10% of this had been converted, so 10% of 300 is 30, so that means we have 270 centimeters cubed remaining, which is left behind. If we add on the 20 onto there, because this is the volume of ozone as well that was created, then that should give us a total volume of 290. And so the answer is C. So that's quite a tricky one, actually. Okay, next one, number 12. 1.4 grams of an alkene gave 3.77 grams of a dichloroalkane on reaction with chlorine. What is the molecular formula of the alkene? So what we have to do, we'll just write down what we've got first. So we've got 1.4 grams of alkene. And then we have 3.77 grams of dichloroalkane. Okay, and then what we have to do, because obviously we need to try and work out the number of moles of some of these substances to work out the MR of the alkene, that's the ultimate goal, we need to work out the number of moles of alkene. And we can't do it from these numbers, but what we can do is we can actually work out the mass of chlorine that was added to this, because we know the MR of chlorine, because it's Cl2, because we formed dichloroalkane. So from that, then we can use our molar ratio to work this out as well. So the mass of chlorine produced is 3.77 minus 1.40 grams, because that's the mass of dichloroalkane, and subtract away from the mass of alkene, and that will tell us the mass of chlorine, which should be 2.37 grams of Cl2. We can work out the number of moles of chlorine. So the number of moles of chlorine is mass over MR, so that's 2.37. The molecular mass of chlorine, using your periodic table, because it's Cl2, is 71, 35.5 individually, so multiplied by 2 gets you 71. And then if we put that into our calculator, we should get 0.033. That is the number of moles of Cl2. Now, the equation for this, it's always going to be one alkene to one Cl2 will form one dichloroalkane, because it's an addition reaction. So it's a 1-to-1-to-1 ratio. So that means we have the same number of moles, of Cl2 as we do alkene. So we can use this number to work out the MR of the alkene. So to work out MR, it's going to be the mass divided by the number of moles. So the mass of this, we said, was 1.40 grams, divided by the number of moles, which is 0.33, and then we should get a total molecular mass of 42. And then if we look down here, all we have to do is find the one which has a molecular mass of 42, and that should give us C3H6. That should be that number right there. Okay, right. So the next question says the standard enthalpy change for the combustion of graphite is minus 393.5 kilojoules per mole, and that of diamond is minus 395.4 kilojoules per mole to the minus 1. What is the standard enthalpy change for the reaction below in kilojoules per mole? Okay, so this is relatively straightforward. All we do is we take the total mass, the total energy, which is minus 393.5 of graphite, and we subtract that away from the enthalpy of diamond, and we just find the difference. That's all we're doing. The enthalpy change is just the difference between the two values. So we're going to put minus 393.5 minus 395.4, and then if we put that into a calculator, remember this here would turn into a positive, so we're just adding the two together. And if we put that into our calculator, we should get plus 1.9. Now, if I put these back to front, I'd get this number. So be really, really careful. You're starting from this one here, and you're subtracting it away from this when you're working out enthalpy change. So especially with that one, you've got to be a bit careful with that one. Okay. Right, number 14. Okay, it says the standard enthalpy change of neutralization when an acid reacts with an alkali is the number of kilojoules released by the. Now this is a neutralization reaction, so we're producing water and salt. So really these ones is not really we're not talking about these ones here. But you should know the definition, and the definition is actually the formation of 1 mole of water, not 1 mole of salt, because salts can vary depending on the acids and alkalis we're reacting. Water doesn't. It doesn't matter what acid or alkali you're using, you're always producing water in neutralization. So we use this one, and so that is the definition that we're using, which is B. Okay, and number 15 says consider the following bond enthalpy values. We've got a set of bond enthalpy values here. Here's the reaction. So this is hydrogen peroxide forming water and oxygen. So it's a decomposition reaction. And it says the enthalpy change in kilojoules per mole is, and all we have to do is bonds broken. So we're going to work out the energy here. So this is going to be, you can see we've got an OO, sorry, here, which is 146. And we're going to add that to, we've got 2 of these, which is OHs, so we've got 2 times by 463. We're going to subtract that away from, this is bond forming, so we've got 2 OHs being formed, so it's going to be 2 times by 463. And then we're going to add that to, now this is half an O double bond O, so this is going to be 496 divided by 2, which is that one there. Now if we work these little bits out here, so we've got, it's normally a good idea to do this because sometimes the calculator doesn't really like it. So 926, which is this bit here, and this bit's going to be plus 248. If we add these two numbers up together, we should get 1072. If we add these two numbers up, we should get 1174. Subtract them two numbers away, and we should get minus 102 if you put all that into your calculator. So the answer is B. Sorry, not B. Top one, minus 102, not plus 102. Okay, so we subtract these two numbers together because that one's bigger than that one. There you go. Right, so that's question 15. There you go. So you can see the answer there. Okay. 16. So it says, using the data in the table below, calculate the standard enthalpy change in kilojoules per mole for the reaction between carbon disulfide CS2 and oxygen shown in the following equation. So you can see here, here's the equation here. They've given us a set of data, and the data is formation data. This is a classic sign of a Hess cycle. As soon as you see this table here and you see an enthalpy change of formation, this is a Hess cycle. So with a Hess cycle, all you do is you write out the equation, which is the one they've given you, which is CO2 plus 2SO2. Formation, the data they've given us is formation, so we draw arrows up to show the formation of our products, and these are elements in their standard states. So we're going to put carbon, solid, oxygen, which is a gas, and we've got sulfur, which is a solid as well. Okay, we don't need to worry about balancing these at the bottom. These ones must be balanced at the top though, because that's going to give us the biggest effect. So okay, so we need to look at the formation of CS2. So CS2 is plus 110. 110. Formation of oxygen is an element, so it's 0, so we don't need to worry about that. Formation of carbon dioxide is minus 390, so put minus 390 there. And we're going to add that to the formation of 2 moles of SO2. So SO2 is 2 times by minus 290. And so if we add that up, we should get, on this side, we should get minus 970. On this side, and obviously this is 110. Now we want to work out this number here, or this arrow here. So we're going from here to here. We're going to go against the arrow here. So this is going to be minus 110. So we'll just bring in this calculator just to show you how it works. So this is going to be minus 110 because we're going against the arrow. And then we're going to go with the arrow here. So that's going to be minus 970. We should get minus 1080, and so that is our final answer, which is the D, which is that one there. With these cycles, the reason why we went around this way is because we want to get from here to here. This is the value we want to work out. So all we're doing is finding an alternative route. It's like a diversion really. So you can see there's like a roadblock. So this one we can't get from here to here using this route here. So we go via this route and with this route. When we go against an arrow, you flip the sign around. So that's how this Hess cycle works. So they're pretty neat actually. Okay. And then question 17. It says, which of the following represents a step in the mechanism during the reaction between ethene and hydrogen bromide? So this is just a mechanism that you need to know. You always produce a carbocation intermediate with these reactions. So the only one which is a carbocation intermediate is this one here. This one's a radical formation, so you need UV light. So this is not the one that we're looking at. So it's this one here, which is C2H4. There's your ethene plus hydrogen bromide will form your carbocation intermediate plus Br minus. So that's the one you just need to try and remember. Okay, and then part B, it says the mechanism of the reaction between ethene and hydrogen bromide is, well, ethene, obviously these reactions are addition reactions, so we're adding HBr to this, so we need to look for an addition one, so we've narrowed it down to A and C, and HBr is an electrophile because it has the delta positive hydrogen, the delta negative bromine, and you've got an electron rich area in the alkene. So this is going to be an electrophilic addition, which is on there because the molecule we're adding has an electron deficient zone. So it's an electrophile. Okay, right. And then on to the next one. So let's drag that down. So it says, which of the following pairs are cis-trans isomers? So we're looking for the groups which are on the same side of the carbon double bond. When I say same side, I mean top and bottom, not like this. So we're looking at this one here, and we're looking at this one here. And you can see these two aren't, but these two are. Now, the reason why these are isomers is because this double bond can't rotate. Can't spin that double bond. It's like in a fixed position, and so because it's in a fixed position, if the Cls are in this position, they react differently to if they're in this position. So this one is cis because the chlorines are on the same side, and this one is trans because the chlorines are on the opposite side, like transatlantic. So this one is 2 and 3. There you go. And the last question for section A is what is the systematic name for the hydrogen for the hydrocarbon shown below? So for this one, we need to find the longest carbon chain, and you can either do like this, or you can do straight across. I would do straight across because it looks a bit easier to see. You can see here we've got 1, 2, 3, 4 carbons, so we're looking at a butane molecule. So straight away, it's between A and B, and you can see here that we've got a methyl group hanging off the second carbon, a methyl group hanging off the third carbon. So this is going to be 2,3 dimethyl butane. So this one is actually B. So that's going to go there, and there we go. So 20 marks in total for section A, all multi-choice. So let's go on to the more full answered questions now. Okay, so this is question 20, section B. So it starts by saying crude oil is composed mainly of alkanes, which are saturated hydrocarbons. Define the term hydrocarbon. They're basically looking for a compound that is made of carbon and hydrogen only. So we'll put that on there. And that's important, the only bit on the bottom there. Okay, so part 2 says state what is meant by the term saturated as applied to a hydrocarbon. If it's saturated, we say it's saturated with lots of hydrogen. So if you're going to have lots of hydrogens, you need single bonds. So what you need to say is you need to say that the molecule contains only single bonds. You could also say at this point that they contain no double bonds. That would still get the mark as well. So you can see it's just one mark for each. Okay, So the next question says crude oil can be separated into fractions. What property allows crude oil to be separated by fractional distillation? Well, the key thing is that crude oil has a range of boiling points because it's different hydrocarbons, different sized chains. So you can put either one of them really. So we'll put down here that we have a range of boiling points. Can't spell properly. There you go. So a range of boiling points. Or you could say you have different sized molecules, anything like that really. Okay. Okay, right. So the next question. So it says many chemists are of the opinion that we should use fuels such as biodiesel rather than petrol and diesel. So just one reason to support this opinion. Well, there's loads of reasons here. We'll put a few down. We can say that it's more sustainable to use biodiesel. You could say that biodiesel is a renewable fuel. Anything along the lines there really. You could say that biodiesel is carbon neutral. Or you could say saves fossil fuels, anything like that really. Saves fossil fuels, or you could say saves finite resources or anything like that. So anything like that really will get the mark. I put 4 there, but you only need 1, so that gets you the 1 mark there. So not too bad. Okay. Okay, so this is part C. It says a molecule of a hydrocarbon X can be cracked to form 1 molecule of pentane, C5H12, and 2 molecules of ethene only. Deduce the molecular formula of X. Right, so how you need to work this out is basically look at the products you've made and count the number of carbons. So pentane has 5 carbons, 2 molecules of ethene. Ethene has 2 carbons in. We've got 2 of them, that means we've got 4 carbons. So 4 plus 5 gives 9. And because we know it's an alkane, where it's a hydrocarbon, it's been cracked to form this. Add up the number of hydrogens, so you've got 12 hydrogens there, 4 on each ethene molecule, so that means 8 for both of them. So if you add all that up, you should get 20, C9H20 for that one. Okay, so this is part 2. It says give one reason why cracking reactions are carried out in industry and suggest why high temperatures are used in this process other than to speed up the reaction. So the first thing I suppose we need to identify for the first mark is that we have a greater demand for shorter molecules. Or you could say more useful products, or because normally these shorter chain ones are actually more useful because we use them as fuels instead of long chains which are used as oils and lubricants, etc. So more useful products, or you could say to make alkenes, because when you crack alkanes, you make alkenes which can be useful for polymers and plastics and things like that. So anything to do with that, that's the reason why we crack the reactions. And we need to suggest why the high temperatures are used. So for the second mark, because it is 2 marks, we need to say that we need a high temperature to break the covalent bonds. There's a lot of strong covalent bonds in these hydrocarbons. So we'll put that on there. So we need a high temperature to break the CC, or you can say the CH bonds. And you could also say something like overcome high activation energy if you want as an alternative, if you prefer that kind of answer. So overcome high activation energy. So anything like that will do, and that gets you the 2 marks, so it's not too bad. Okay, so the next one says butane C4H10 is a hydrocarbon which is used as a fuel. It is a gas under standard conditions. Explain what is meant by the term fuel. A fuel is something that produces energy, so simple as that. So we'll put a substance that produces energy, or you can say heat as well, because that's what the fuel does. So obviously you burn the fuel and you get heat from it, so we can use it to power things. Okay, so the next part, it says write an equation for the complete combustion of butane under standard conditions, include state symbols. Right, so that's really important. State symbols, and it's under standard conditions. So we need to make sure, because we've got 2 marks here, we actually get a mark for the equation and 1 for the state symbols. So this is butane, so butane is C4H10. Now butane is a gas under standard conditions. We're going to react this with oxygen, and because it's complete combustion, we're going to produce carbon dioxide and water as the standard products. Oxygen is a gas, and so is carbon dioxide, and liquid for water. Not gas. You can't put gas here because it does come out as a liquid. So we're going to burn these. So we're going to burn this. Now we need to make sure obviously this is balanced. So the quick way of doing it is check the number of carbons. 4 carbons must mean we must have 4 molecules of carbon dioxide. 10 hydrogens must mean we must have 5 molecules of water. So these are always based on this, the number of carbons and hydrogens here. And then obviously you then just tot up your oxygens, and you should have 6.5 O2 there. Now you get 2 marks for this, 1 for your state symbols, so we'll do this in red. So you get 1 for your state symbols, and then 1 obviously for your balancing of your equation, so that gets you the 2 marks there on the side. Okay, right, on to the next part. Okay, so it says write an equation for the incomplete combustion of butane to form carbon monoxide and water only. State symbols are not required. So there's only 1 mark. So we're going to write our fuel, C4H10, and this is going to react with oxygen. And we're going to produce carbon monoxide, CO, and water. So they've actually told us the products that we're forming. So that's really important. Again, number of carbons 4, so you must have 4 carbon monoxides. 10 hydrogens, so we must have a 5 there. And all we have to do is make sure our oxygens are balanced. We've got 9 on this side, so that means we need 4.5 on this side of the molecule there, and that gets you that mark. Okay, so next one. Under what conditions would you expect incomplete combustion to occur? You'd expect it under limited oxygen, so a limited supply of oxygen. There you go. So that's just 1 mark. Or you could say not much oxygen or limited supply of air or anything like that. Okay. And next one is a calculation. So it says butane can react with bromine in the presence of ultraviolet radiation according to the following equation. And there's the equation there. Calculate the atom economy by mass for the formation of C4H9Br. And we use this expression. This is our atom economy expression. And we have to use the periodic table as a source of data. So let's just push that up there. Okay. So what we have to do is we should work out the molar mass of the desired product and then the molar mass of all products. So let's put that on there. So MR of des product. So all we have to do is the desired product is this. Now if we use our periodic table, which we've got here, you can see that carbon is 12, and we've also got hydrogen's 1, and then bromine, which is on here, bromine has a mass of 79.9, as you can see on there. So we're going to add all that up, and we should get, so we've got obviously 4 times by 12, which is the 4 carbons, plus the 9 for the hydrogen, plus 79.9 for your bromine. And if we add all that up, we should get, let's put this into our calculator. So we've got, let's put that on there, 4 times by 12, plus the 9, plus 79.9, and we should get 136.9. So we're going to put that in there. Okay, that's the MR of our desired product, and then we've just got to work out the MR of total products. total prods. Okay, obviously we've worked out the MR of this already, so then we just need to work out the HBr. So this is one of the products. So we'll put 136.9. We're going to add it to a mass of 1 for the hydrogen, and then the Br we said was 79.9. Add all that up. So there's the 136.9 is already in there, plus the 1, plus the 79.9. And that should give us an answer of 217.8. Go. Stick it into our equation. So that's the molar mass of the desired product, which is 136.9 divided by 217.8 times all that by 100. And then we should get our final answer. Stick this in here. 136.9 divided by 217.8 equals, times that by 100. There you go. 62.85. So we'll put that on there. Well, that would round up, so that would be 62.856% if we had to round that up. And just write our final answer in the bottom here, which is just going to be 62.9% if we do it to 1 decimal place. So you get 2 marks for this. You get 1 mark for working out the total mass of desired products, so everything, and then 1 mark obviously for getting your answer. Make sure it's substituted in the right place. So there you go, there's your 2 marks. Okay, right, on to the final section. Okay, so it says, describe the mechanism for the reaction between butane and bromine that forms the products given in the equation below. So we've got the equation here, and it says in your answer you should include equations for each step of the mechanism. Curly arrows are not required, so what they're looking for is a radical reaction then. And we have to name each step occurring in the mechanism. So anything to do with adding a halogen onto an alkane, and where we're not required to write curly arrows, this is where we need to use the radical mechanism. So this is just like a list of equations and breaking them up into the different sections. So it's 7 marks, there's quite a bit here. So we'll just push that up so we've got plenty of blank space. Right, so the first one, with all these ones, is initiation. You get 1 mark for writing that, for naming the steps, so that's pretty straightforward. And what happens in initiation is the halogen first is broken up using UV light into 2 radical 2Br dot, and there's your first mark there. The next one is, once you've formed the radical, we then have something called propagation. So propagation is to kind of allow, is like the chain reaction bit. It allows the reaction to proceed. So we bring down the halogen radical from here, and we put this down here. So we must have Br dot. Now in propagation, it's always radical and non-radical. And as soon as though we're going to react it with butane, and we're going to add a radical to butane, then that is our next product, or next reactant, sorry. Now, this is a bit like past the radical. The radical disappears from here, and the hydrogen drops off to form HBr, because that was one of our products. So, as a result, the radical now sits on this molecule here. So that's going to be C4H9 dot, and we're going to produce HBr as well. And always in propagation, the radical product of the previous step forms the reactant for the next step. So you drag this down here. So that's going to be C4H9 dot. And ultimately we do need to form a haloalkane. So we need to have an unreacted halogen that hasn't actually been split into a radical. And this is going to form our final product, which is C4H9Br. And we're also going to form as the radical now jumps onto here. So we have a Br dot. And again, the product of this step must be a reactant in the first step because it is a chain reaction. So all these little checking points to make sure that you're getting it correct. Okay, there's your propagation. The final step is termination. Now, it hasn't specified what termination reaction we want, and there's actually 3 different types of termination. So we could have, and you get any one of these would get the mark, really. So termination is always two radicals joining together. So you can have that one, Br dot plus Br dot. You could have another radical in here with C4H9 dot, and that can react with Br dot. So actually the termination reaction in itself can form a heteroalkane, so C4H9Br. Or you could use C4, you could have two C4H9 dots reacting together. And that will form C8H18, which is octane. So we can form this, could be a fuel as well, that we could use it. So this is a 7-mark question. So in terms of the mark breakdown, you get one for, say, an initiation, one for the equation, one for, say, propagation, one for that equation, and one for that equation. So you've got 1, 2, 3, 4, 5 marks. 6 marks for, say, termination, and 1 mark for any one of these 3. You only have to write one of them, though, for the termination step. And so there we go. That gets us all our marks. We've got 7 marks there. The whole question for this was out 21 marks. So not too bad. On to the next question. Okay, so this is question 21, and it says lattice energies can be calculated from experimental data using Born-Haber cycles. In the table below are the enthalpy changes needed to calculate the lattice enthalpy of sodium oxide Na2O, and they're giving you all the enthalpy changes and the values there. So the first thing it says is to define the term lattice enthalpy or lattice energy. So lattice energy, it's for 2 marks. So we need to say enthalpy change. That's a very important point. So this is an enthalpy change that leads to the formation of 1 mole of a compound from its gaseous ions. Alright, so this is for 2 marks. Now the really important point here is that the 1 mole bit is really significant. So it leads to the formation of 1 mole of a compound, which keeps everything in standard ways, and then of a compound from its gaseous ions. So the ions must be in the gaseous state, in other words. So they're your 2 marks there, they're your marking points. So it must be 1 mole of a compound, and they must be in its gaseous ions. They're your 2 main points really for this question. Okay, right. So on to the next part. Now, this is where we're going to still need the table for this bit. So it says, write the correct letters from the table of data to label the Born-Haber cycle below. Okay, so we just need to use this information that we had before in the previous table to write some letters on here. So let's start with this bit here. So you can see we've got, here's our elements in their standard states, and we're forming the salt, which is down here, which is this one here. So this is sodium oxide. So if we bring in the table, we can see that this one should be the enthalpy change of formation of sodium oxide because we're forming it. So we're going to put F in there. Okay, so the next one, you can see here we're going from sodium solid to sodium gas. So this is an atomization process. So this is going to be enthalpy change of atomization of sodium. This is D. Now, you can put D, or you can put something like 2D if you want, because effectively we're atomizing 2 sodium atoms. The next one, we're going from sodium, sodium gas to sodium gas, there's no change there. Half O2 gas to O gas, so this is atomization again, but this time this is atomization of oxygen, so half O2. So we're going to put that there, and that letter was E. Okay, and the next one, we're going from this one here, so we're going from sodium gas as an atom to sodium ion. Again, we're doing it twice because we're going from 2 sodium atoms to 2 sodium ions, so we're ionizing twice. So this is ionization, first ionization of sodium. So that's going to be C. And again, you could put 2C if you want, because we are doing it twice, so that would still get the mark. Okay, the next one, now we've got all the electrons. We're now going to add some of these electrons to the oxygen. we've only added one electron here to the oxygen. So this is electron affinity. And this is the first electron affinity of oxygen because we're adding an electron to oxygen. So this one should be A. And this one here, you can see that we're adding the second electron to form O2 minus. So that one is going to be the second electron affinity, which is B. And then we're going from here, from the ions in the gaseous state, down to form your solid salt. These are ions in the gaseous state. So this one is the lattice energy of sodium oxide. We're forming the lattice from ions in the gaseous state. So this one is going to be G. Okay, so there's all your 3 marks there. So it's not too bad. Make sure you know your definitions. Right, and the next bit says we need to calculate the lattice energy of sodium oxide, enthalpy change G in kilojoules per mole. So this is the brilliant thing where this cycle really works quite well. So we're going to do a lot of backwards and forwards here to make sure it fits in. Okay, so we want to work out this value here going down. So we need to get from here to here, but treat this as like a roadblock that we can't go down that way. So we need to take a diversion. And when we go against an arrow in a cycle, we need to change the sign or the value of this here that represents this arrow. So this one was B. So B was the second electron affinity of oxygen, which is plus 790, as you can see on there. So because we're going against the arrow, we're going to change the sign to minus 790. So we're going to write it all down here. So we're going to start with minus 790. And we said that was B. And the next one is A. So this is A here. A had a value of minus 141, as you can see here. But we're going against the arrow here, so that's going to be plus 141. So we put that there, plus 141, and we said that that one was A. And then we're going to come back up onto the top of this cycle here, as you can see here, and we're going to come against the arrow here. This is C, but because we've got 2 of them, we need to multiply whatever number this is by 2. That's really important. So C here was plus 496. We're going against the arrow, so that turns it to minus 496, but we have to double that. So we're going to do 2 times by minus 496. Okay, and that one was 2C. Okay, and then we come on to E. You can see here we're going against the arrow for E. So E is plus 249. So against the arrow, that means minus 249. Okay, which is going to go there. And that one was E. And then we've got D. So D is plus 108. We've got 2 of them. And we're going against the arrow, so that's going to be minus 218. So 2 times by minus 108. So we've got 2 of them. And this one we said was 2D. 2 lots of D. Remember, we're doubling it because we have 2 atomization there. And then we come on to F. Now F, we're going with the arrow to get to our final destination. So F is just minus 414, so we keep the sign as it is. So that's going to be minus 414. There we go. And we're then going to work all that out. Stick it into our calculator. So let's bring the calculator in here at this point. Okay, so we're going to have minus 790 plus 141 plus 2 times by minus 496 minus 249 plus 2 times by minus 108, close the brackets, minus 414, first equals, and we should get minus 2520, and that is our final answer. So that's where we can use the cycle. It comes in very useful actually. So this is going to be minus 2520, and that's kilojoules per mole. And they've given you a spot at the bottom to write your answer in, so we'll may as well put it in there as well. Minus 2520, and that's in kilojoules per mole. And so that gets you 2 marks. Obviously, 1 mark for your equation, make sure that's right, and then obviously your answer needs to be correct as well. Make sure you calculate it correct. So that's how you can use the cycle to do that. But I suppose the key points here to remember is that you've got to remember to double some of them if you are atomizing twice. So be really vigilant for that as well. And as long as you're going against the arrow, you need to change the sign. And so that's pretty much it, really. Okay, right, on to the next part. Okay, right, so it says predict whether the lattice energy of magnesium oxide, MgO, is more or less exothermic than the lattice energy of magnesium sulfide, MgS. Justify your answer in terms of the sizes and the charges of the ions involved. Right, this is really important. So we've got to talk about both of these things here. So the first thing we need to say really is just make the statement that magnesium oxide is more exothermic than magnesium sulfide, MgS. Okay, and the reason for this is because we need to say that the S2 minus, this ion here, is larger than the O2 minus ion. So we're talking about the size here. That's the first thing. So we're going to add that in there. So we're going to say the S2 minus ion is larger than the O2 minus ion. Okay, and we need to also comment on the fact that both of these charges are exactly the same size, but S2 minus has a lower charge density than O2 minus because S2 minus is a bigger ion, so it means that charge is spread over a larger area. So that's the next thing, and this is talking about the charges bit on here. So we're going to add that bit in there. So we'll just put on there. So we put charges and both ions are the same. And you can say the S2 minus has a lower charge density. Okay, and then the final thing really is we need to link this back and say, well, right, okay, so why does magnesium oxide is more exothermic than magnesium sulfide? So we need to say that O2 minus ions, as a result, these ones here will form a stronger electrostatic attraction than S2 minus because it has a higher charge density and it can attract stronger to the magnesium ion than sulfide can. So that's our final point. So put that in there. So O2 minus forms stronger electrostatic Alright, so 4 marks. You can see I've tried to split it up so you can see the mark structure. So you get 1 for saying that magnesium oxide is more exothermic, 1 for talking about the size of the ion, that S2 minus is larger than O2 minus, 1 for talking about the relative charges on them, that they are the same, but we have a higher charge density on the O2 minus than we do on S2 minus, and then finally topping all off and saying that the O2 minus ion forms a stronger electrostatic attraction than S2 minus. That's a really, really important term. But there we go. You can see total number of marks for question 21 is 11 marks. So on to the next question. Okay, so this is question 22, and it starts by saying nickel is an element in the D block of the periodic table. Complete the electronic configuration of a nickel atom using the SPD notation. Right, so we'll get the periodic table over, and they've been very kind to us, and they've given us 1s2 to start off with. So here's the periodic table, and we're going to find nickel, which is down here. So this is going to be 1s2 have already been given, 2s2, 2p6, 3s2, 3p6, 4s2, 3D, 1, 2, 3, 4, 5, 6, 7, 8. And there we go. That's your electron notation. So let's write it down. So it's going to be 2s2, 2p6. So 1s2, 2s2, 2p6, 3s, 2, 3p6, 4s2, 3d8. These can be either way around. They're not really that bothered. So either one would get the mark. Okay, so then next it says a sample of nickel is made up of 3 isotopes. The percentage abundances are shown in the table below. So you can see we've got different abundances of the isotopes. Calculate the relative atomic mass of nickel. Give your answer to 2 decimal places. Right, so let's nudge it up there. Right, this 2 bit's important. We've got to give it to 2. If we don't, we won't get all the marks. So this is really easy to do, really. The AR of nickel, all we have to do is multiply these 2 numbers together and divide them by the total abundance. We add these numbers up, we divide them by that. In this case, this is percentage, so it's just out of 100. So let's start with the first one, which is 58 times by 69.02. Add, that's the 58 there, times that, and then add 60 times by 27.32. Add 62 times by 3.66. And then divide the whole lot by 100 because it says a percentage. Okay, so let's bring our calculator over. So we have 58 times by 69.02. Add 60 times by 27.32. Brackets. Add 62 times by 3.66. Close the brackets. Equals. And then we need to divide that by 100. And then we should get 58.6928. Needs to be in 2 decimal places, so 58.69. Okay. There you go. And you get 2 marks for this. You get 1 mark, obviously, for writing your equation at the top here. And you get 1 mark for your final answer. So it's 2 marks. So it's not too bad. Okay. Right. The next part. Alright, so this is part C. And it says nickel reacts with carbon monoxide, CO, to give a compound nickel carbonyl NiCO4. And there's our equation there. Calculate the volume of carbon monoxide in decimeters cubed measured at room temperature and pressure. That is required to react completely with 5.87 grams of nickel, given as the relative atomic mass, and the molar volume of gas as well at room temperature and pressure, which is 24 decimeters cubed. Right, so the first thing, obviously, we need to work out the volume of carbon monoxide, but to work out the volume, we need to work out the number of moles of carbon monoxide. Now, we can't work out the moles directly because we don't have the right numbers, but what we can do is work out the number of moles of nickel first, because we have a mass and we know its relative atomic mass as well. So that's what we're going to do first. So we're going to work out moles. There's a saying that I like to use is, if in doubt, work out the moles, because from the moles you can work out so many things from the moles. So the moles is, in this case, it's mass, which is 5.87. And that's going to be divided by the relative atomic mass of nickel, which is going to be that. Let's bring in our calculator. This is going to be 5.87 divided by 58.7. Stick that in. There you go. 0.1 just to confirm that. So that's going to be 0.1 moles. And then from that, we can now work out the number of moles of carbon monoxide. It's a 1:4 ratio. So let's make it really clear. Moles of carbon monoxide. And that is just 4 times by this number of mole here. We don't really need a calculator for that. So that's going to be 0.4 moles. That's the number of moles of carbon monoxide. And then finally, we can then work out the volume of carbon monoxide, because we just take the number of moles times by this molar volume of gas, which is 24. So it's going to be 0.4 times by 24. And then bring out our calculator for that one. So put that over there. So this is going to be 0.4 times by 24. There you go, 9.6. Okay. Uh, 9.6 decimeters cubed. And that is the units that we need it to be in anyway, because it said decimeters cubed at the top there. Alright, okay. So 3 marks for this. Pretty straightforward where you should get the marks from. One there, and one there. Make sure you draw your units as well, or write your units, should I say. Right. Okay, so the next part of this question says calculate the number of carbon monoxide molecules present in the volume of gas you calculate in C part 1. Right, so there's the volume of gas that we've used there. So to work out the number of molecules present, we need to find out the number of moles of carbon monoxide. And we need to multiply that by Avogadro's number, or Avogadro's constant, which is this here. So all we do is we take the number of moles, which is 0.4 times by Avogadro's number, 6.02 times by 10 to the 23, huge number. And if we bring out our calculator, let's shove that across to there. So this is going to be 0.4 times by 6.02 times by 10 to the 23 equals there. So this is going to be 2.408 times 10 to the 23. So it's a lot of atoms. So 2.408 times by 10 to the 23 molecules, should we say, molecules of carbon monoxide that's present. So there we go. 1 mark, so just for the answer. Okay, and then for the next part. Okay, so here you can see it's talking about nickel 2 nitrate, NiNO32, can be made by several different methods. But method 1, nickel oxide NiO, was reacted with dilute nitric acid according to the equation. There's our equation there. Calculate the volume of 2 moles per dm cubed dilute nitric acid in centimeters cubed. That's important. There's a little bit here. You need to remember that. That was required to exactly neutralize 1.494 grams of nickel 2 oxide. Use the relative atomic masses of nickel to be that, and oxygen is that. Right. Okay, so the first thing we need to do is, because we want to work out the volume of nitric acid, to work out the volume we need the number of moles of nitric acid. Now we can't work out the number of moles of nitric acid directly, so what we have to do is work out the number of moles of anything on this equation, because from that we can then work out the number of moles of this. Now fortunately we can work out the number of moles of nickel oxide because we have a mass of nickel oxide and we have an MR, so we can work out the moles. So you can see with all these equations, they're all starting in a very similar way, which is working out the moles of something, and then that leads you on to calculating other things. So it's quite a strong pattern, as you can see. Right, so moles of nickel oxide, so this is going to be mass. So moles is mass, which is 1.494, divided by the molecular mass of nickel oxide, which is going to be 58.7 plus 16, which is going to be 74.7. And then if we put that into our calculator, so we have 1.494, and we're going to divide that by 74.7, and that's going to get us 0.02, and that's the number of moles. 0.2 moles. Okay. Then we need to then work out the number of moles of nitric acid. Now you can see here, let's just write this down. Moles of HNO3. Okay, so the moles of nitric acid is going to be the number of moles here times by 2, because we've got a 1 to 2 ratio there. So this is going to be 0.02 times by 2, and that's going to get us 0.04 moles. And now we know the number of moles, we can then work out, the volume of nitric acid, HNO3. Okay. Now the volume is calculated by taking the number of moles and dividing it by the this. So let's put this on here first. So 0.4, because we need to work it out in centimeters cubed as well. So to work out the volume is the number of moles divided by the concentration. The concentration is 2 moles per decimeters cubed. So we're going to divide that by 2 first, and that's going to get us 0.02 decimeters cubed. All right, but the next thing we have to do is we have to convert this to centimeters cubed, because it did ask for centimeters cubed. Now, I can imagine a lot of people might miss that bit out. So to convert to centimeters cubed, we just need to times this number by 1,000, and that will get us 20 centimeters cubed, and that's the volume. Now, this is out of three marks. So obviously, you can see here we got the 1 mark there, 1 mark for working out the number of moles of nitric acid, and then obviously 1 mark for the volume of nitric acid that we've had to calculate. Okay, right. So next question. So it says method 2. So remember, this is talking about 2 methods. A volume of 25 centimeters cubed of 2 moles per dm cubed of nitric acid, HNO3, was transferred to a beaker. Solid nickel 2 carbonate, NiCO3, was added until it was in excess. Why was excess nickel 2 carbonate used? Excesses of things like this is to ensure that everything reacts suitably. So we added an excess carbonate to make sure that all of the acid reacts. So we'll put that in there. So to make sure all the acid reacts. All right, okay. And then the next one, it says, why must the beaker be much larger than the volume of acid used? This is quite a tricky one. This is like how science works. You go back to this equation. It did say that we're producing, because it's an acid and a carbonate, we're going to produce a gas as a result. Remember, acid plus carbonate will produce salt plus carbon dioxide plus water. So because we're producing a gas, we're going to need a larger beaker, because you might get a little bit of overspill because the gas has been produced, the gas has been released. Now, the marking criteria really needs to include either the words you've got fizzing or you've got a gas that's released. So you need that extra volume to take into account that you are producing a gas and you might get a little bit of overspill. But these are the key things that you need to put in there. The emphasis is on the gas released rather than the overspill, because it's just examining you on the area that this is an acid and a carbonate, and that will produce carbon dioxide, salt and water. Okay, so that gets you the mark there for saying that a gas is released as a result. Okay, right, and on to the final part of this question, or the final parts, shall we say. It says, write a balanced equation for the reaction between nickel 2 carbonate and dilute nitric acid. We've got to include state symbols for this as well. So let's make a start. So we're going to put nickel carbonate, which is NiCO3. Nickel carbonate is a solid, and this is going to react with nitric acid, so HNO3. So this is acid plus base, and this will produce salt. Now the salt is the metal from the base, and that reacts with the non-metal part of the acid. So nickel is 2 plus, nitrate is 1 minus, NO3 minus. So we need 2 of them. So we put NO3 2 to make sure that balance. That's important, that little bit there. We also produce water, obviously, and we also produce carbon dioxide. Right, carbon dioxide is a gas, water is a liquid. This is in aqueous. This is dissolved in solution, so it's got to put AQ. And all acids are aqueous. That's really important. So that's aqueous there. So there's our state symbols. Now to make sure it's balanced, you can see we've got 2 nitrates over here, so we need a 2 in front of there, like so. And then everything else should be balanced. Okay, so we get 2 marks there. You get 1 mark for actually writing your correct species, which are these bits here. And then you get 1 mark for making sure that it's balanced and the state symbols are included as well. So that's for the second mark there. You get 2 marks for this. Okay, and then on to the last bit. Now it says, for method 2, describe the practical steps that you would take to obtain pure dry crystals of hydrated nickel nitrate with the 6H2O, so this is just hydrated salt, from a mixture of nickel 2 nitrate solution and unreacted solid nickel 2 carbonate. Right, now this is really important, this bit. Unreacted solid. So the first thing we need to do is we need to get rid of that solid, and the first step is to filter off any of that solid. So that would be your step number 1, is to filter, and they're really looking for that. So really look for that bit there. So filter off any solids So in this case, we're talking about the nickel carbonate. Because we have some excess, that's the first thing we need to do, is to get rid of that. Then once we've got that, we then have a solution left. Now, to get crystals, we need to drive off as much of that water as we can. So the next step is to boil the majority of the water off. Not boil it dry, but to boil the majority off, to leave a small amount of water left behind. So that's the next thing, is to boil. We boil, and we do that to remove excess water. Okay. Then once we've done that, we should have a small amount of water that's left behind, really concentrated solution. So then what we do is you might have done this in school or college, is to leave this on the windowsill and let some of it to evaporate. So we'll put that on there. So leave to evaporate. And allow crystallization. So this is effectively the water that's left behind is going to evaporate naturally over a reasonable length of time, and we're going to get some crystals starting to form over about a couple of days. But that's not all of it. It did say we need to obtain pure dry crystals. These crystals have still got water absorbed into them, so what we need to do is we need to dry them crystals, and that is the final stage. So we need to dry the crystals off. Okay, so you can just put them in an oven, and that should dry them off there. Right, this is 4 marks. Obviously, you've got 1 mark for making sure you say filter. Boil gets the 2nd mark, so boiling it all off. Evaporation to allow crystallization to occur will get you the 3rd mark, and then drying the crystals is the final step. Again, they've really specified what they wanted here: pure dry crystals and unreacted solids. So these little bits here within the question give you a little bit of a hint from the start to the end bit, and this bit you just need to add in the middle there. But you see, you get 4 marks. The total mark for this question is 18 marks, so not too bad at all. Okay, right, on to the final question. Okay, so this is question 23, and it says, this question concerns the periodic table. An atom of argon has a mass number of 40. Complete the table below showing the numbers of subatomic particles in this atom of argon. Use the periodic table as a source of data. Right, so it's basically wanting to look at argon 40. We need to work out the number of protons, electrons, and neutrons in there. So this is relatively straightforward. So if you find argon, argon's here. You can see we've got 39.9 as the mass number and 18 as the proton number. So the number of protons is 18. The number of electrons is the same as the number of protons, so that's going to be 18. And then to find out the number of neutrons, we round that to 40. So do 40 minus 18, and that leaves us with 22 neutrons, and that's how we work it out. So let's pull this back in. So this is going to be 18 electrons and 22 neutrons, and so that gets you the 1st mark. Okay, so part B. An atom of potassium has a mass number of 39. Explain why argon is placed before potassium in the modern periodic table. Well, Mendeleev was the person who discovered the modern periodic table that we have today, and he put the elements in order of proton or atomic number, not mass number. So the mass, it's not an order of mass, it's an order of atomic or proton number. So we're going to write that on there. So we're going to put position in the periodic table depends on proton, or you can say atomic number. Alright, okay, so that's why it's in that particular order. Okay, right, so argon obviously has less protons, it has it has 18 protons compared to potassium, so therefore it would be placed before potassium, which has a few more than argon. Okay, so part C, and it says, in the context of the periodic table, explain what is meant by the term periodicity. Now, it's 2 marks here. So the whole point of periodicity is you're looking for a trend or some kind of pattern. So we'll put that there. A trend or pattern. And I suppose the main thing is the whole point of periodicity is that it's the whole thing is repeated. So it's a rather long R. So is repeated across each period. So it's 2 marks here. So they're looking for a trend or some kind of pattern. Would actually get you the first mark. And the second mark is by saying that it's repeated. That gets the second mark there across each period. So yeah, very important that you should know that, really. Okay, right, on to the next part. Okay. So it says here, the graph shows the variation in melting temperatures of the elements across period 3, sodium to argon, of the periodic table. So we have melting temperature here, and we have the elements listed along the bottom there. It says, name one of the elements above that is composed of simple molecules at room temperature and pressure. All right, so let's just nudge that further up there. A simple molecule is one that is covalent and has a low melting point, and it must be a molecule as well. So the molecules here that we can include are anything like phosphorus. We can include sulfur in there as well, or we can have chlorine. Any of them will do. Here we are here. There's phosphorus, sulfur, and chlorine. Argon is not included because argon isn't a molecule, it's an element. It exists on its own, whereas these ones do, which this is Cl2. Sulfur forms an octahedral, an octagon shape, and phosphorus is P4. So these ones are all little molecules, whereas argon is on its own, and silicon is massive. That's a completely different structure altogether. Okay, the next part. It says silicon has a giant atomic structure. Explain how this structure results in the high melting point and the high melting temperature shown on the graph. Okay, so what we need to say then is that silicon is actually a giant covalent structure. So it has loads of strong covalent bonds. So we're not talking about weak intermolecular forces like these molecules here. So that's the first thing we need to say. So, and the next thing, obviously, because it is talking about the melting temperature, so it has lots of strong covalent bonds, and therefore a lot of energy is required to break the bonds. All right, so in terms of marks, then. It has a lot of strong covalent bonds. Obviously, that's a really important marking point there. And then the energy bit is important as well. So that's the second marking point there. So lots of strong covalent bonds and a giant covalent structure. And therefore, you need a lot of energy, or a large amount of energy is required to break the bonds apart, which effectively means that you can melt it. So there's your 2 marks there. And then on to the final question of the paper, which is this one here. It says, explain why the melting temperature of magnesium is higher than that of sodium. Right, so this is a 3-mark question. Now the idea is that we're looking at 2 metals here, but magnesium is in group 2 and sodium is in group 1. So a metallic bond is the bond that they want you to talk about. So with a metallic bond, just as a reminder, you have positive metal ions and you have a sea of delocalized electrons. Now the metallic bond is the attraction between the sea of delocalized electrons and the positive metal ions. And so if you have a bigger attraction between them two, then you're going to have a metal with a higher melting point, so, or melting temperature, as they say here. So in this case, magnesium, we need to first start off by commenting on the ions that we have, I suppose. So Mg2 plus has a greater charge density than Na plus or sodium plus, and the reason why is because Mg2 plus ion is smaller than the Na plus. So this means you have more of a charge in a specific area than you do with sodium. Now, this big charge density is going to have a big impact on how well the delocalized electrons are attracting to the positive metal ions, and that's going to have an effect on the strength of the bond. Okay. Not only that, but magnesium, because it gives up 2 electrons to be delocalized, and sodium only gives up 1, you've actually got more electrons being delocalized, which again increases the charge difference and hence the strength of the bond. So the next point really to say here is that we have more delocalized electrons with Mg2 plus than Na plus. Okay, so that's the key thing there. So more electrons being delocalized, and then the final thing is obviously trying to wrap this up. Is then you need to say really that we have a stronger attraction between Mg2 plus ions and the electrons than you do with sodium. So obviously because of this increased more delocalized electrons with Mg2 plus and the fact that magnesium 2 plus has a greater charge density, it means we have a stronger attraction between the delocalized electrons and the positive metal ions, and that is effectively the metallic bond. But there you go. That's the end of the whole paper actually. So this question had 10 marks in total. Just looking at the marking structure, you can see you obviously get 1 mark for talking about charge density, or by saying that the magnesium ion is smaller than the sodium one, either or, put a slash there. You get 1 mark for obviously talking about the delocalized electron issue here, and then the last one is talking about the attraction, because obviously it is talking about metallic bonding, or it wants you to talk about metallic bonding. But there we go, all the marks sorted out. That's it for now. Bye bye.